Alrighty, so let's talk about IR. Okay, so the IR is based on a simple principle or explores a simple characteristic of bonds, and that's that bonds are not, they're not rigid. Okay? What that means is that when we build our model kit, we build them with these plastic balls and then this plastic stick, right? And when we put those two atoms together, they look like, okay, here they are, they're this far apart, they're always this far apart, they're hard, that's like this hard, rigid thing, right? But that's actually not what bonds are like. Bonds are actually, one of the models we use, we talk about them acting like springs, but the main point is that the atoms are moving like this. We call that a vibration, okay? This particular one where the distance between the atoms gets bigger and smaller, we call that a stretching vibration. There's also a vibration where if you have an atom, I'm sorry, this looks totally weird with my face on there. You have an atom, there's an angle between those bonds. That angle gets bigger and smaller. Okay, that's called a bending vibration. And these are just natural things that occur. Okay, so for example, what I want to show you is if I have an atom, there's a bond between it. I have an atom, okay, and there's a distance between those two atoms. Well, those atoms can be I don't know if that's exaggerated enough, but right? So I'm basically trying to show that they started here, they moved out to there, then they moved back in, right? That's a stretching vibration. Okay, there's also a vibration that looks like this. I'm going to really exaggerate this so you really see it, right? Where the angle sort of defined by three atoms, right? Two bonds and three atoms gets bigger and smaller. This is a bending vibration. There's actually more than one type of bending vibration. This particular one is called scissoring. Just for completeness sake, in the full set of notes from last semester, I think I showed all of the different vibration types, but if you didn't see those, someday I can do it. But scissoring, because it looks like scissors, right? You're doing like that. Okay. Generally, I would say the most common type of vibration that we look at and interpret is a stretching vibration, but there are some useful bending vibrations if we get a little advanced in the IR. Okay. All righty. Now, here's the thing about these vibrations. So the vibrations are these cyclic processes. They go back and forth. And so we have a term to describe the speed of this cycle. Like how long does it take to go from smallest to biggest and back to smallest? Okay. We call that the frequency. All right. We're going to talk about frequency again in a little bit. But the thing about the frequency, okay, is that the faster that frequency, the more energetic the vibration. Does that make sense? But there's another way that that vibration can be energetic. I'm sorry, I know that this is so weird with my face in the way here. But basically, if we go at the same speed, okay, but we go bigger. So it's the same speed, but it's bigger. That's called the amplitude, okay? It's like the size of that vibration. And the bigger the amplitude, the more energy, okay? So molecular vibrations have a very interesting property. It's a property that's shared by almost all really, really tiny objects. And that is that unlike us, where when we get in our car and we put the accelerator, we could go 41 miles per hour, we could go 41.1 miles per hour, 41.2 miles per hour, whatever. We have all these different speeds, basically any speed that we could go. Really, really tiny objects are restricted to only certain energies, only certain speeds or whatever, okay? So they might be able to go 20 miles per hour and 40 miles per hour and 60 miles per hour. And if they were to increase, they would go without even going any speed in between. They'd be going 20 and then all of a sudden they'd be going 40. Okay? We say that systems like that where it's not continuous, right? Where there's only certain allowed values, we call those systems quantized. And that is one of the important characteristics of 20th century physics, right? Is they started studying quantized systems as opposed to 19th and 18th century physics where they studied continuous systems, right? Where you had any allowable value. Okay, everybody cool with that? Quantization. Okay, so bond vibrations, molecular vibrations are quantized. When you have a bond with two atoms and it's vibrating, it is only allowed to have certain energy values. And that is super useful to us. That's what allows us to do IR spectroscopy. Okay? So I have a picture here on my screen. This is a picture that I think, well, if any of you guys are chemistry or physics or engineering majors, you will see this again. The rest of you probably won't. Okay, but I want to introduce it for those people who might see it again and give it an explanation so that maybe you'll kind of get it the next time you see it. It took me a long time to understand this. Didn't understand it first time I ever saw it. Okay, so here's what they're doing. They're showing a bond. So we have, you know, an atom here, and then we have this distance D. That's R, capital R, okay? How far apart are these two atoms? Okay? And it turns out when you take two atoms and you put them together, if you stretch them apart and then hold them there, their potential energy goes up. If you push them back to where you started, it might go down. But then if you try to push them too close together, the potential energy goes up again. All right? And so this basically represents the potential energy change, like when we take two atoms that are really far apart, okay, where R is very big, and then we start putting them together. So in fact, actually what I usually think of this as is one atom is right here, and then the other atom is moving in, and the distance here, this is R. Does that make sense? So think of one atom being fixed, you're moving the other atom. How far apart is it? Okay? Everybody cool with that? That's what the x-axis is. And then what we do is every time we move an atom, we measure the potential energy, and we put a plot, and that's what this blue, I'm going to make it blue, what this blue curve is, right? It's how much energy does that have? Okay? Everybody good with that? If you have a question about that, speak up or whatever. Okay, so here's the deal. When we look at a normal bond has what we call a bond length. And the bond length is actually the average R of the atoms. In other words, the atoms don't have one fixed thing. They go kind of bigger, they go kind of smaller. So when we talk about a bond length, what we're saying is they go bigger and smaller, but on average, they're about here, right? That's in between the biggest and the smallest. Does that make sense? And that would be the lowest energy, the lowest potential energy that bond can have. But most bonds don't have that lowest energy. They have a little bit of extra potential energy, okay? And so what happens is, because they have a little bit more potential energy, there's like an amount of potential energy. They're going to start there. Then remember, potential energy often in physical systems gets converted to kinetic energy. So here's what happens. They're at this high potential energy. They start moving together, right? So as they're moving together, so they're starting out here. I'm going to put it really far, okay? They start moving, they move together, right? Until they're at that perfect bond distance. But when they're at that perfect bond distance, they've taken all that kinetic energy or potential energy, they've converted it to kinetic energy. So now they're at that perfect distance, but they're moving really fast, right? So they start here at the high energy, they're not moving. They start moving together, they're moving really fast. That means they move past that perfect distance. They move together, right? And as they move together, they start pushing each other apart, which slows them down, but increases their potential energy again until they get, again, to that same high potential energy they started with. There's no friction in this system, so energy is conserved, okay? And they stop moving. But now the potential energy pushes them apart. So they start moving again, right? And their energy goes down, and then they go back up like this. So I'm trying to use the height as sort of a representation of the potential energy, right? Do you see how they're doing that? They're moving from a wide distance to a narrow distance. That's what this graph is trying to show. Do you see? It's saying pick a potential energy level. That's the widest they're going to be. Now they start moving, they reach that thing, then they move up until they stop moving at the other end of that curve, right? And then they move back. So they're moving back and forth. Everybody cool with that? Okay, so here's the point. Remember, I told you they're only allowed to exist at certain potential energies. So this would be the lowest one. Then this is a potential energy. Then this is a potential energy. So what this means is they're going to vibrate between certain fixed allowed distances, but the speed of their vibration will be constant. And if we look then, what we have here, that distance there is a delta E, right? It's a change in energy. So I can have them vibrating this far apart. If I put in energy, now they start vibrating this far apart. Same speed, just wider, okay? That's the quantum effect. Now, the significance of that then is that to change that vibrational energy, we have to put in exactly the right amount of energy. Exactly delta E. If it's bigger than delta E and it doesn't match any of those distances, it won't be absorbed, it just goes right through them. Okay? So what we're doing is increasing the amplitude of the vibrations. So bonds absorb IR radiation, causing a change in the amplitude of the vibration doesn't change the frequency.